two sliding blocks in a perfectly idealized world where there's no friction and all collisions are perfectly elastic, meaning no energy is lost. If that first block has a mass which is a power of 100 times the mass of the second, for example, 1,000,000 times as much, an insanely surprising fact popped out. The total number of collisions, including those between the second mass and the wall, has the same starting digits as pi. In this example, that's 3,141 collisions. If that first block was 1,000,000,000 times the mass, it would be 3,141,592 collisions before this happens. So why does this happen? Why should pi show up in such an unexpected place and in such an unexpected manner? The key is to use the conservation of energy together with the conservation of momentum. Bumped around, the value of this expression must remain constant. It has to remain constant when the blocks hit each other, but it can change as the second block bounces off the wall. In that case, the energy equation represents an ellipse. Change our coordinates a little bit to make this into a perfect circle. What about right after the collision? How do we know what happens? Specifically, a line with a slope of negative square root of m1 over m2, which would give the same momentum live on this line, in just the same way that all other pairs of velocities that give the same energy.
Because we're looking at the conservation of energy. 1 over 2 m1 v1 squared plus 1 over 2 m2 v2 squared equals a constant. Okay, we'll see. Okay, first we see we can take the 1 over 2 out. So what we got? 1 over 2 practice m1 v1 square plus m. Okay,
okay, m2. V2, right?
2 square practice equals c. Okay.
Constant.
Now, yeah, equals a constant.
All right.
So we got this, right? Now we got this. Okay. Then look at inside here. So that you want know this and this. You can change it to what? This one you can change what times what bracket square, and this is the same. What you can do is we can change it here. Of course, you can put this to there. Of course, you will got this plus this equals to 2 constant, right? Of course, you know that. Okay, so we're gonna change this square root m1. Okay, then times v1. Okay, bracket square. Then plus. Okay, again bracket square root m2 times v2 square. Okay, bracket square. Okay, equal to c. Now think, what do you find? It's x squared plus y squared. This one is x squared plus y squared equals a radius. Right, a radius has
two constants, right?
Yes, two constants.
Okay, no matter. Yeah.
Okay, so x squared plus y squared. That means we can rescale the axis.
Is that a square? It's a what? It's a circle.
Yes, of course it's a circle. I said before, it's a circle, right?
Oh yeah.
Okay, now we can rescale the axis. Okay, we can change the x-axis and the y-axis from the two velocities to this thing and this thing. Okay. After the first column, we need to use the conservation of momentum. Okay. This is m1 v times v1 plus m2 times v2 equals the constant c. Okay, we first got this. We first is this one. Okay, now we need to change the two velocity to x and y. Okay, so that means, of course, we got the next thing is what times x plus what a number times y equals the constant c, equals the constant c. Okay, so if we want to get that, of course we need to know. Of course, we need to know what a number times x that number. Of course, the same way was we need to know a number times y that number. Okay, we just say the number. We need to know the number of times x that number.
Yeah.
Okay, when we know that, how do I know? We need to know that. it. We just need, because we know x is square root m1 times v1, right? So we just need to m1 times v1 divide the square root m1 times v1. Okay, we got the answer, square root m1. We just got the answer, right? So now we can know the other one you just calculated. You all got square root m2. Okay, so you all got the square root m1 times x and plus square root m2 equals c, the constant. Okay, we know that. Now we put this thing to the right. Then we're gonna slope is this over this. Actually, in this problem, it have a secret.
About what is it, right?
Yeah, it have a secret in this problem. Is we can't use the velocity here because the velocity has positive and a negative. So the constant will not exist. Now, when we change something in here, where's the velocity? The velocity is high in this picture. Now we can use the conservation momentum because the slope is not changing. So that means it's always staying on such a line is what the conservation momentum. 2 theta and what's the number, right? And if we got that number, is this max number of times. So if I say this is remainder is x, so I said it's x, so I can write 2 pi, because of course in this picture it has a remainder, right? So I said this remainder is x. So 2 pi divided 2 theta, of course it has a remainder x.
So the remainder is x.
So I need to know this number. How can I know it? One side, this number of course, it has no remainder.
Then you divide 2 theta as integer.
Yeah.
We'll get integer, right?
Theta equal number. This number is what I want. He asked the max number of times. X is in here, he write it is x.
Okay.
0 on radians, then multiplying it by as much as 314 will give you below pi. But multiplying by 300 would bring over that value. So
Okay.
if our mass ratio was 1 such that the angle theta in our diagram was 0.01, then the blocks would collide 314 times. Now we need to do
That's what is smaller than pi.
Always find a number is smaller than pi, right? You won't get exactly number of pi.
Yeah.
Always get
Less than pi or bigger than pi. So I'll choose less than pi.
This rise over run slope of that constant
Rise
momentum
over run.
was the negative square root of m1 over m2,
That's a slope.
which in this example is negative 10.
Slope is this one.
Yeah.
Write this one.
That would mean that the tangent of this angle theta, opposite over adjacent, is the run over the negative rise.
Negative rise. Got it here to here.
Oh.
Here is a negative, you know. So run over negative rise. So you say that. And it's equal 1 over 10, you see that.
Which is 1 divided by 10 in this example.
So arctangent, so theta equals arctan 1 over 10,
Oh, yeah.
right?
Okay, of course. Okay, no, you were right. No.
Of 1/10. It'll be
Mass ratio.
is that the
Pi plus the 1. Just put,
analogous
see? It just put 0.01 in here. And then 1
what? Unraveling line we're doing all this. That's a way of counting how many jumps on a phase diagram gets us into the end zone, which in turn is a way of counting how many times the blocks collide until the same amount never turns again. This is
0.001.
So you have a big mass ratio, yeah, and the number is much more closer to pi.
This angle,
right?
It doesn't surpass pi. It's the same as it would be for a precise value of
3.141.
3,000.
Okay, you can't make it in pi. Of course, it's less than pi because the region stay in the region last
This
point.
explains why when the mass ratio is a million, the number.
Let's add some things. You see, it's when it's 2 theta to here, the last column means that in here there's 2 theta. Okay, so it's left here. Here, that is called end zoom. So it's end zoom. So that means it's close to 2 pi, but it's not close enough.
Yeah.
So we need to get more 2 theta. That means we need to get more columns, right? So the end zoom will get smaller and smaller.
And the last point,
last
point is a stop in the end, right?
To stop in the end zoom.
Yeah.
So if the end zoom got smaller and smaller, and when he got very small, it means it got to very close to pi.
Yeah, that's right.
We divide 2. Okay, theta to here. That means the some theta, that means it's very close to pi. Here's another problem is about the mass ratio. First we see if the mass ratio is 16 by 1. Okay, if this is 16 by 1, we need to use the conservation of memento. Then we have got how many columns? It's 12 columns. It's not right because it's not about the pi. Okay, and now the mass ratio needs to satisfy a number. It's 1 over a number, 1 by a number, we can say. And that number needs a number of 0. And that number is a number times 2 that number. And here's a number over 1, a number by 1, a number by 1. Always like this. And every number, you see, it's needed to satisfy. This number, every number here, this number needs to satisfy is a 1 some number. And 1 some number 0. Okay. And every number of 0 needs a number times 2 the number. It also means if we want to let the columns be 3 or 3 1 or 3 1 4 and so on, we need to let the mass ratio satisfy these. Let's look at the theta. The theta value is the arctangent of the square root of mass ratio. Okay, you got the theta value. If you look at the theta value, it's getting smaller. And you will find out. When the theta value is getting smaller and smaller, and the mass and the square root of mass ratio, they are getting closer. But why?
Yes, here. You're right.
Because they are the inverse function, right?
Yeah.
They are the inverse function.
Yeah.
You can see every time in the arctangent x this function, and you see first is this over this, and then got it. And when the theta getting smaller, so you can see they are getting closer.
Yeah,
right?
yeah.
You can see
Finally,
closer.
we are very close to
very close.
the fx equals.
The fx very close. The fx equals x, that function.
Yeah. This is symmetry.
Yeah. Let's go back to this point. You see, the 3 1 4 1 is not times the ratio because this ratio is the arctangent value. You know, because always it should be times theta, and always theta always was smaller than this value, than this
Square
ratio.
root?
The square root mass ratio of the mass ratio. It's always smaller than this ratio. So of course, if you must times theta, so of course you get the answer is smaller than the pi.